Okay, I'm going to start out today to review because it's been, like a million years in COVID time, and so nobody remembers what any of these are, I'm sure. So let's start back with flip-flops and latches. And we talked about latches first, right? And the whole point of these is in order to design circuits that remember, because we spent the first portion of the class talking about circuits that were combinational, which means that the outputs depend strictly upon the combination of the inputs. Now we want to talk about sequential circuits, which means one thing can happen after the other, and it remembers what the sequence was, what happened before. How do we get here, right? And so the base building block we have of this is the SR latch, which as a component we would draw like so. We would build it out of NOR gates like this. And the idea is basically that if set is 1, it sets the Q to 1. If reset is 1, it sets the Q to 0. If neither of them are 1, if they're both 0, then whatever it used to be is just going to sit and chase around this kind of interloop network, and it's going to hold on to that value. If set and reset are both 1, they're both trying to make Q 1, which means we don't really know what it is. If you do the analysis of it in kind of the ideal world, what you'll get, I believe, in this one is that Q and Q bar, right? This is Q bar, so not Q, are both 1. Is what I think happens in this one. But we could do the analysis and figure out what it actually is doing. But in general, we just say, don't do that because it doesn't make sense. It's a bad situation to be in. If I don't care what Q bar is, if I don't need to use it, I don't draw it. But there is no difference in complexity between having it and not having it drawn in that block because it's here for free. I can access it. There's no problem with it. Then if I take a couple of these and I stitch them together, right, I start sticking them together, then I can start getting flip-flops. And the difference between a flip-flop and a latch is simply that the flip-flops have a clock, meaning that the output won't change until whatever signal is on this pin goes from a 0 to a 1. It's looking for a change on the rising edge. Or if we did a little inversion bubble, that means it's looking for the falling edge, right? And the point of a clock is simply to synchronize commands, to make sure that we're doing things at a known time, at a reliable time. And something that came up in the last lecture that is kind of a good point is why? Why do we want synchronous? Because it turns out that doing what we call asynchronous design has some major benefits. And it's an active kind of field of research of how do we design asynchronous circuits, because we can get some performance benefits out of it. But it turns out to be hard because we like to know exactly when things are happening rather than having them happen as fast as they can and see where that gets us, right? And the obvious example for this is, and we'll do this in the very first lab of digital systems, is you take an old keyboard and you plug it into a computer and you push the letter K. How does it know that you pushed K? Well, what it does is it sends a string of 1s and 0s. It sends 8 characters, 8 1s and 0s. And that, what we would say waveform might look like this. 1, 2, 5, 6, 7, 8. Okay, and then the question is, what is it, right? What is, if I send that, what does the receiver get? And it's the question it becomes, well, it could be 0, 0, 1, 1, 1, 0, 0, 1. If my clocks talk the same speed. However, if this clock that is on the receiver runs really fast, it's going to think it's 1, 1, 1, 1, 1, or sorry, 0, 0, 0, 0, 1, 1, 1, 1, 1, 0, 0, 0, right? It's going to read too fast. So we need something like a clock to tell 2 different parts, 2 different components, when they're doing things. When are you supposed to react? When are you supposed to read? When should you add this number to this other number? Because you don't want to do it too soon. So that's the clock, right? It's just to coordinate the time between 2 different parts of the system. That's what this little flag says, is it's expecting a clock. And it will change on the rising edge. So if we were to have a clock for this one, it would be something like, well, that clock is going to get, right? This rising edge would correspond to that first 0. And then we'd have 8 clocks in that if I wanted an 8-bit character. We can build SR flip-flops. It's not as common. They do the same thing. If they're 0, 0, we take Q at n+1, meaning the next rising edge. The next time that I see an update, we stay what we used to be, Qn. So the next Q stays the previous Q. If we reset, it goes to 0. If we set, it goes to 1. If we do that, it is X, which if we want to talk more in like Vivado terms, right? U is a good character, undefined. We don't know what it is. Then we can easily build the D flip-flops. D flip-flops are the most prolific, they're the most common, and they're also the most easy to use because it simply says at each clock edge, the next Q is whatever the D is. That's all. Whatever data was, let's save it, right? This is basically memory. It's what we would call a register or the beginnings of a register. If I stick multiple of these in parallel and I save many bits, then it's a register. And it remembers what I had. The difference, and this is really nice, if I want 1-bit flip-flop, there we go, right? If I want to turn this into an 8-bit register, as far as the diagram is concerned, done. That now implies that there are 8 D flip-flops in there that can store 8 bits. So I can put an 8-bit number into that, a rising edge of the clock happens, and it saves it in there for me. JK flip-flops are really useful and interesting because they have a lot of the same properties of the SR without the unknown nature, right? So similar, if it's 0, 0, we remember what we used to be. If it's 0, 1, well, the K acts as the reset and the J acts as the set. And if they're both 1, instead of going undefined, it acts as a toggle. It just inverts whatever it used to be. Take the old one and flip it. And what's nice then is if I stick 2 of these together, the J and K input, if I attach them together, I get a new kind of flip-flop. Because if they're attached, I can only remember or flip. That builds us the T flip-flop. Or T for toggle, right? Which just says if there's a 1 here, the output flips. If there's a 0 there, it doesn't. It stays the same. Now, these turn out to be incredibly useful because if we look at the number sequence, right? Even before I taught you guys how to count in binary, I taught you truth tables, right? And we can build them with a pattern, which says we want to go 0, 1, 0, 1, 0, 1, 0, 1. And then the second one is 0, 0, 1, 1, 0, 0, 1, 1. Which in a way is saying that if in each column I could have a clock that is running half as slow as the previous column, and they ran, I would be able to build what's called a counter, right? I want to be able to count from 0 to some number, or from some number down to 0, or -10 to +10, whatever my range is to count. T flip-flops are kind of the easy way of doing this. They end up almost trivializing the design of a counter. VHDL will do it even easier for us, but the counters that we build here tend to be really easy. And I'm going to grab out my notes to make sure that I do this in the right order so that it makes sense. So the T flip by itself, if you consider T to be enable, this is now a 1-bit counter. It counts from 0 to 1, right? Nice and easy. If I take another T flip-flop and I want to count, well, I'm going to use my enable for it as well, because I don't want to count. I don't want the second one counting if my first one's not. And then I'm actually going to leverage Q bar here, and I'm going to use not Q as my next clock. Okay. Let's build another one. T, Q, clock, not Q. And then each of my Qs Q0, Q1, Q2 correspond to that truth table. But let's test it, right? Let's prove that this works. Yeah.
So I have a quick question. Other than not Q, is it basically like an inverter in a way? Because
the T flip-flop?
Yeah.
Yeah, it's an inverter with an enable.
Okay.
It's a clock synchronized inverter.
Okay.
With an enable. Yeah. So let's go ahead. I'm going to draw some timing diagrams up here because that's going to be good review, right? It's good to get back into the one of the most important tools that we have in analyzing circuits. I have dots to guide me and I still struggle to draw straight lines. Okay. So let's just assume that enable is going to be on. We'll just say enable is 1, so I don't have to use a whole line for it, because if it's not enabled, just nothing happens. The next thing is, in the case of a T flip-flop, I have to give you the starting values. I have to tell you what the output Q starts at. Because if I say it's undefined and you want to toggle it, what is not undefined? It's still undefined, right? We still don't know. And so we're going to say that all of my Q0 to Q2 starts at zeros. We're going to assume that we have a reset signal, right? It's not unreasonable to assume that there's a reset signal on each of these. You can build really easily. You reset it, it goes to 0. We turn on the enable, it starts counting. Well, let's go ahead and look at what happens if we have Q0, Q1, Q2. I'm actually going to skip one row because I need a clock first. Clock, Q0, and then I'm actually going to plot not Q0 just so that we can see it. And then I'm going to do Q1 and Q2, but I'm not going to plot their dots. All right, so let's suppose that the clock goes like so, starts at 0, rising edge. I said Q0, Q1, and Q2 all start at 0. That means not Q0 starts at 1, right? And so now we have to remember that devices aren't ideal, right? They're made out of gates. And in fact, it's made out of several layers of these gates with associated logic. So it's not unreasonable to think that these T flip-flops, I think, travel through like 8 gates before they get there if you've optimized it. So it's got a lot of delay, right? We call that delay clock to Q, meaning how long between the edge of the clock does it take after the edge of the clock to Q changing to whatever it needs to be. Okay. Well, we're also going to have TSU. That's the setup time. So if I draw a clock here, this is clock. So what's going to happen is the time that you need to have the data, the input stable before the clock happens is TSU. The amount of time that you need to stay stable after the rising edge is called T hold. Setup and hold time. And this is simply because a clock doesn't look like this. Not really. It looks like that. Take some time for it to charge up. And the faster we go, the worse it looks. In fact, if you start pushing the edges of a clock, they start doing basically a sine wave, right? They can still work as a clock, but we need to be very careful with timing once they get there. There's also other issues that you're going to see diagrams. I don't delve too much into it in this class. We'll talk a little more about it. You'll see them drawn like this, or even like that. This is what we just call jitter, which is to say our devices aren't perfect. There is some amount of unpredictability about when that rise even starts. And then there's the rise time. So we have to rely on some device physicist who gave us the components to tell us what is the setup time and hold time, and then we just make sure we meet those. We don't have to understand yet why that's happening. We just have to trust that the other engineers know what they're doing, and as long as we meet those, it will behave correctly. If we start violating these timing requirements, it breaks. Okay, so the clock to Q, the little t is time. The clock to Q, a lot of times you're going to start seeing me reference it in terms of the period, capital T. Remembering that the period is equal to 1 divided by the frequency. Frequency being how often does a rising edge happen per second. How many times per second does a rising edge happen? That's the frequency of a clock. Or falling edge is the same thing, right? So that's what the capital T stands for, is the period of the clock. So in this case, from here to here is the period. So let's assume that there's some amount of clock to Q delay in this circuit. And in fact, I'm going to define it as the clock to Q, C2Q, is going to be 1/8 of a period. So this is just abstracting away, so I don't have to write exact times up here, whether or not this is a 20 nanosecond period or a 100 nanosecond period. We're just going to talk about it in terms of the ratio. So if this is my period, that means half a period, right? Quarter period, yeah, half, quarter, eighth. So it's a quarter of a half, right? Period, or half of a half, yeah. So we're gonna get down here, and that's just how long does my Q take to update after the rising edge. I just want to get a little bit of non-idealities in here because it actually turns out to make things a little bit easier to draw than if they're perfect. Okay, so this rising edge happens. The Q0 is enabled, right? I said the enable is on. So after a little bit of time, it steps up. Comes over here, next rising edge, a little bit of delay, it toggles, little bit of delay, it toggles, little delay, it toggles. Well, the Q bar in this case, Q0 bar, is the same thing. We're going to assume same delay, which is a pretty reasonable assumption. It's just the opposite. Now here's what's nice. Remember how I pointed out that if that middle column has a clock that is half the speed of the first column's clock, then it would work. See this Q bar? It's half speed. We've slowed it down a whole bunch. So now this Q1 starts at 0 and in fact stays 0 all the way until this rising edge, right? Because this Q0 is here. This is Q0 bar. That's the new clock. Original clock, is here. We've made a new clock here. Q1 is going to react, same concept with the delay. Here. Well, what this means is because we're using Q1 bar as the next one's clock, this is Q1. We can't in our head imagine what Q1 bar looks like, right? It's the inverse of this, meaning Q2 doesn't do anything, it doesn't react on this rising edge. It reacts on this falling edge because we're looking at the inverse of this, right? So that means that Q2 follows along until this happens. A little bit of that delay, rising edge. Then we can check, is this a counter as I said it is? Well, I'm interested in Q0, Q1, Q2. So here I have 0, 0, 0. And I'm going to go bottom to top, right? Because I want to talk about it in terms of number. I want Q2 to be my biggest number. So Q2 is still 0, 0, 1. Then we have 0. Let's see, make sure we're doing this right spot. I got to go over to the next clock, don't I? Sorry. So 0, 0, 0, the clock happens. We have 0, 0, 1. The next clock happens. We have 0, 1, 0. The next clock happens. We have 0, 1, 1. The next clock happens. And we have 1, 0, 0. There's my counter. This is what's called an asynchronous counter. It's asynchronous, despite the fact that each of these devices are synchronous devices, right? They're clocked. The fact that they don't share a common clock, they each have their own clock, means they're asynchronous. They're not timed together. Okay, so you'll notice that if we look at this far right rising edge, then we had a little bit of a delay here, right, between the clock and the rise. And then this was the new clock, and we had a little bit more delay and a little bit more delay until this was our initial change, but our output has shifted all the way over here. It has an accumulative delay, which is to say at this point, if I ever get to the point where I've done 8 in a row, if I've stuck 8 in a row together, that means that my last one, my 8th toggle, won't update until the first toggle has started changing to the next number, and we will never see a correct number. So we've inflicted a speed limit on our 8-bit counter. So if we slow it down, we can actually end up adding more because the time will stay the same, because the devices don't really scale with the period. This is kind of just an abstraction, right? So we can slow devices down and make bigger counters, but we do have a limit on the speed of, or the number of bits in our counter based on the delays. Okay, and that's going to be true for a lot of things. So we're going to have, you know, when you had your full adders, you start sticking together, they start having that chain delay, and you end up with issues if you're trying to build big adders and make them go fast. You just can't do it. Okay, so we can also build synchronous counters, ones that all of the devices are linked to the same clock. And this is the one that you've all forgotten, but I did talk about not last week, 2 weeks ago.
Really all have an enable and
Correct. But it's been a long time, so let's go ahead and just review it. I won't go through the timing on this one since we've done it, but I think it's not harmful to reevaluate. Oh, actually, before I do that, there is something really cool that we can talk about with this one, which is, let's say we want to count down. How do we do it? Well, it turns out in a countdown timer, I just break these connections. I don't need the Q bars at all. This is now a countdown timer.
You don't need to invert the first clock.
No, and let's talk about why. Let's assume that this starts at 0, right? Well, if this all starts at 0, 0, 0, when the first clock happens, that causes this Q to go to 1. Because we're going 0 to 1, that makes this a rising edge, which makes this a 1, which makes this a rising edge, which makes that a 1. So on the first clock, I go from 0, 0, 0 to 1, 1, 1, which is a countdown, right? If I have 3 bits and it loops around, that's countdown. And it just goes from there. It counts down from there, which is really nice. I think I end up doing that as a homework question, so I'm not going to do all the timing on that one because it's kind of an interesting countdown timer. Okay, the synchronous counters, though, this is just back to the review. We've done these before. They're still based off of the T flip-flops, the toggles. But in order to make it synchronous, the clock has to be common to all the devices. They have to share a clock. Otherwise, it's not synchronous. Then we're still going to treat it like we have an enable here that funnels into the first one. And then the second one, we're just going to add an AND gate that says, if we're enabled and Q is 1, then we can toggle. And the next one says, if the previous Q was 1 and this one is 1, then we can toggle. And then we just start repeating that architecture. This is now a synchronous counter. And they share a clock. What's moreover, this is actually a faster clock. Faster counter, we can run it faster because instead of having to wait on the delay of, let's say this was 8 devices, 1. So this would be roughly 8-ish times faster theoretically, because it doesn't have that accumulation of delays through the flip-flop path. It's just through the gates, the AND gates. There's still a limit, right? It's not instantaneous, but it is faster. So that's all the synchronous counter is. A little bit different design, a little bit of complexity in order to get more speed, right? That's one of those design trade-offs I'm always talking about, which is if we want something to go faster, it probably has to be more complicated. If we want it simpler, well, we have to either use more power or, you know, some other trade-off. We have to look at the things that we can adjust. So now let's go back to, let's say that I want to build a BCD counter, okay? A counter that's around BCD, and you're given, so if you recall, BCD is binary coded decimal, okay? Binary coded decimal just means that we're going to be lazy about the way that we represent numbers. I actually need to keep going for a moment. Where I want this to represent 0, 1, 2, 3, 5, 6, 7, 8, 9, and then my 1, 0, 1, 0, right? The thing that comes next is I don't care. So I'm not going to do it because I just want my hex character, my hex code to represent one digit, basically, one decimal, right? Because if I'm in hex, then I use all of them, all 4 bits. But if I'm using decimal, then I just throw away a couple of those. I have a little bit of wasted logic, which is, it's okay. And so we end up with a counter. We would go build this logic, and I'm going to have Q0, Q1, Q2, Q3, a 4-bit output. I want an enable. I want a signal called load, and actually I'm going to put the load down lower. Where's the best place to do this? I need a clock load. And then I also want something called load val, which is going to be a 4-bit number that I'm just going to save that way. So I want to be able to assert, if I say 1 here on this load signal, I'm going to pull in whatever value is at this pin. So if I don't want to, it's like a reset. Like if I put 1, 2, 3, 4 zeros into that, right? When I hit load, it is the same as a reset. But if I don't want to reset to 0, I can change it. It's just an option. But let's design for 0. Let's keep it as a reset with 4 zeros for the moment. And we now want to talk about the idea of combining sequential logic with combinational logic, right? We want to utilize them both. So what this is saying is this is going to be just a 4-bit counter. Nothing special. It's not itself a BCD counter. But I want to turn it into a BCD counter. That means that I want to go back to 0 after I see this number. Not when I see that number, but after I see that number. So we have 2 ways of doing this, which is we could either draw the K-map for it. And the K-map is basically going to say, well, I can truncate this to just 0. We'll just understand this an integer that we convert to a different data type, right? And I want to design essentially what we're going to call reset. We're going to plug a code because I'm going back to 0. There's nothing calling. We're going to make this signal called reset. That's what I want to make. And so I can look at it and go, well, let's reset right after I'm done with this 9. If I put my reset on the 9, that means it's going to hit 9 and instantly reset, and we're not really going to see it. It's not useful to us. So we're going to do it one after. Okay, as soon as we're done with that, we reset. That means that everything after there is don't cares because it's resetted. It's never going to get to that point. So it's just don't cares. So that means it's 0, 0, 0, 0. That's 4, 5, 6, 7, 8. 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1. Don't care, don't care. Right, that's our K-map for this circuit that we're building to make the reset signal. And it's looking at the signals Q0, Q1, Q2, Q3 of this counter, right? That's its inputs. The output of the counter is the inputs to some combinational circuit that I want to design to do this reset for me. That means I go ahead and I circle my K-map. I only have 1, 1. That completes coverage. It is also minimized. And and I would need to go and assign and figure out which the Q zeros are where, or because we're starting to get good at this, I just look at it and go, well, the first time that Q3 is 1 and Q1 is 1, that's where I want to reset. So that means let's take Q3 and Q1. That's my reset. Which the K-map is the same answer. Okay, if it's simple, sometimes we can just look at it. And then this is my 4-bit BCD output. And then if we wanted, well, there's an interesting thing that we can do. Is if this wants to power, say, you remember your FPGAs that they have little 7-segment displays, which is the alarm clock style. This can now plug into a BCD to 7 segments, which will then go and tell the outputs what to do in order to display characters 0 through 9. This, right, is called an encoder. It's encoding this counted value to be a 7-segment displayed value. Encoders are one of the things that we talked about 2 weeks ago that I'm sure most of us forgot. But encoders conceptually are really easy. It's just a conversion. How do we change one number representation to another representation? Well, let's say we want to do 2 digits because we have 2 digits on our basis board, right? How do we build a 2-digit counter out of this? Well, it turns out, let's just use the same concept where there's going to have an enable and it's going to, let's just assume it's on for the moment. And that, well, this enable is on, right? We're just going to say, let's always count. Well, what happens on this one is at the same time that I'm going to reset, I may have designed something wrong. We may have to do the timing on this because I was thinking about the reset timing in one specific way of designing it, the way that I would design it in VHDL. But I think the way that this is going to make more sense is because the reset is going to be coded, if we design it as a synchronous reset, that means that it won't reset until the next rising edge of the clock. So this is the design for an asynchronous reset or an asynchronous load. If we were designed for synchronous load, we would attach this to Q0, right? Because then we would want the reset here at 9. But this is the design for asynchronous load. Okay, well, now what happens is this one is going to go ahead and trigger the enable and say, you can now go. And then it's going to have the Q, which is a 4-bit number, just the same. And we're going to build the same type of logic that comes back around and feeds it around. But it's the same logic, really. And now what happens is this goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, passes the enable, and this goes from 0 to 1. Now we're 1, 0. We just made 10.
Let's backtrack just a little bit, but the encoder, is that basically the constraints we do at the end? That's kind of
No, the encoder is a step in between. The encoder is what you did on your exam, where we said, And these of course continue on down, right? But the 7-segment display looks like this. And if I call this segment A, then this is my output LED A. And it turns on if I have a 0, doesn't turn on if there's a 1, doesn't turn on if there's a 2, no 3, there is a 4, not 5, and so on. This is an encoder. The circuit that results from that is it's taking my BCD and turning it into 7 segments. And then I would be like, well, this is now B. What's B? Yeah. So it's translating from binary coded decimal into human visible decimal. Okay. Great. And I just want to make a note, actually, as I think about this more. I designed this reset assuming an asynchronous load. I don't think the dual setup would actually work with the asynchronous load because the enable would exist for such a short period of time that the other clock wouldn't see it. So I would probably redesign this to be a synchronous load in order for it to work. Just so you're aware, if you end up building one of these, be aware that I think it needs to be a synchronous load. And in case you're confused what I'm talking about, let's build something with a synchronous load. Let's talk about it, right? In terms of VHDL, it's probably good to get back into VHDL because I heard you all making up a million different excuses for why you didn't touch VHDL over the break. And it's probably good to get back into that kind of mindset of VHDL is not programming, it's hardware design, right? It's a language that we use to describe to the computer what the hardware should look like. That's what it's doing. It's not programming. So let's say that I want to build a counter. Okay, well, I could reflect on the T flip-flop circuit that I built before, and I could just build a flip-flop, which is really trivially easy. And that was in the homework, I believe. And then, of course, none of you have done it, right? Because it's not due till like Wednesday or something. So you've all put it off till after this. But we can still build, let's see, which one did I decide I should build up? A counter a little more intelligently, right? This is what's nice about VHDL, is I need you all to understand these basic building blocks, but we can leverage other skills and other concepts to make it easier to design. So instead of building a T flip-flop, let's make something called a counter. And I'm just going to start with the architectures begin. Okay. And we'll assume that I've made any other signals that I need. The signals that are coming in to a counter are basically this: enable, load, load val. This is what I'm building. Okay. Let's build this 4-bit counter with let's plan on having it designed as the synchronous load. So this, right, this is going to load when we get to 9, but hopefully it doesn't do that until after it's had a full clock cycle of being 9. Right, we don't want it to skip past the 9. That's what we want to design. So the first thing that we do, if we're designing synchronous logic, is declare a process, right? Because that's what's, or sorry, sequential. Synchronous sequential, that's fine. And then my voice, there we go. We need a sensitivity list, right? When does this process run? What activates it? Well, in this case, let's say clock. And here's the difference, is here is an asynchronous reset. That's what I'm powering here. If I wanted the asynchronous load, I would put load up in this signal as well, but I don't. There is a begin turns out on this board, it's going to be easier for me to put it over here. It's totally allowed. You can actually just begin as part of that same line. I tend to format it down here when I write the code in VHDL just because it's easier to read for me, but this is perfectly allowed. Then we say if reset equals 1, then our Q output gets assigned to, and I'm going to leave a little bit of space here after the Q on purpose, and we're going to come back to this later, gets assigned to 0, 0, 0, 0, right? And we could make a note, a comment that says this is also equal to the same as saying that, because the X in front of it says whatever comes next is hex characters, X for hex. So each, oh, sorry, not 0, 0, 1, 0, right? Because each character is 4. So this is a hex character 0, which is the same as that. Either one of those is a fine way to do it, right? The double dash is the comment in VHDL. We remember this, meaning this code doesn't do anything. It's just a reminder. And now I'm built my reset. Otherwise, else if, right? There's no E in the VHDL. Here we're going to say rising edge of the clock, right? This is important. Don't forget the else if rising edge, because the issue is if you forget the rising edge, the process will activate on both the rising and falling edge of the clock, and things will get weird. It's hard to understand what went wrong. Okay, so now we get that rising edge of the clock. What do? Well, the first thing I want to do is I want to check if there's a load, because I'm designed a synchronous load. So I say if load equals 1, if load is true, right? If I send it back around, then Q gets assigned, oops, I'm going to leave a little bit of space after the Q, gets assigned to, well, whatever load val happens to be. And this question keeps coming up. So Q is 4 bits, right? In that picture, load val is 4 bits. I don't need to do an index on this because it's going to take 4 bits and stick them into 4 bits. Everything works. The only time I write the index is if I'm using some subset of the bits in an array. So like if load val was, if I built these both into one component, then I would, and the load val was an 8-bit input, then I would need to do something like load val 3 down to 0, right? Take the smallest bits of load val. However, this is allowed. If load val is 4 bits, that's 4 bits. This is still okay. It's not wrong. It's just extra writing, right? Else, and this is where we're going to get a little bit weird, which is probably okay. Well, let's do another else if, because I have an enable there. Let's build it. Else if enable equals 1, Q gets assigned to, well, I would like to do this, right? Q plus 1. But the issue is that Q is a standard logic vector, and I can't just add 1 to Q. And the other issue is Q is my output, right? And I can't put outputs on the right side of an assignment statement. That's not allowed either. So this actually has 2 errors in it right now. Is I can't add 1 to a standard logic vector, and I can't put an output on the right side of an equation. So what I would do is up here, before the begin, I would create a new signal. And I'm going to call it QI for integer. I'm actually just going to make this an integer. The way that I do that is I say, Actually, let's do unsigned. It's a little bit easier to convert unsigned, and there's also allowed to add one. Unsigned 3 down to 0. And now I'm going to convert this to QI, this to QI, and this to QI, and this one to QI plus 1. See why I left those spaces before and pointed it out so I could do this conversion. So now this is still allowed. I can still put 4 zeros into my unsigned. I can still take, well, this is not quite right. This one needs a data conversion type, which I'll show you how to do in just a second. And then this is allowed. And then we say else QI stays QI. Right? So if we're load, then load. If we're enabled, count up. Otherwise, stay the same. If you flipped load and enable, you would have a potential problem, which is that if enable came first, then you can't load unless you're not enabled. Because if the first if evaluates, it won't look at any of the other portions of the if statement. It won't look at any of the else's. It just stops. It goes, if this is true, okay, let's do it. It only says if this is true, no, okay, then we'll do this. So when this load evaluates, even if enable is on, it's not going to count up. It's just going to load. It's not going to load and count. It's just going to load because this is an else. Make sense? So the order of your if statements matter. So be careful with them. Think about the steps. Walk them through in your head. Okay, then we're going to write the end if, end process. Okay, that's going to all be down here. I'm going to not write it all. And then I would come up, and sorry, I have to erase this. Let's keep this in mind though. Then I would come up after all of the ends, and I would just write Q, which is my final output. It's assigned to, well, it's going to be QI, but QI is unsigned. So I just write the standard logic vector. I have to write the whole thing out of QI.
Is this coming right before this begin? Or?
No, this is at the very end of the code. That's why I wrote this end behavioral. That's the very end thing that you do, right?
Yes.
This is the last line before that. And this is basically kind of like taking, well, here's QI, and it goes through a buffer to Q, and each of these are 4 bits. But this buffer isn't just a buffer, right? It's actually an encoder that is changing my 4-bit unsigned to a 4-bit standard logic vector. It's just changing the way the number is represented. Same number of bits, minor change in representation. So that way, right, this QI is both, it's an internal signal. And I keep doing that, which is kind of a bad habit because I keep thinking of them as internal signals because that's how I introduce them to you. If you're out in industry, the most common notation for this would actually be Q_S for signal, right? Rather than QI, because QI looks too much like QIN. So the standard, that tends to be QI is input, QS is internal signals, and QO is for outputs. If you go get a VHDL job. It will vary depending on which company you work for, but most companies have like a standard practice of how it's represented. And it turns out if you're in the Ogden, Salt Lake area, it's very similar company to company because there's kind of that, everybody moves between those companies in this area. Not many people run away from Utah. If I'm honest, very few people leave. And so the skills move around and it kind of homogenizes the habits that everyone has, which is kind of useful actually, but you should be aware that's what happens. Cool. There is a note I guess I should make on the rising edge. Just in case you see this code, I will never write it this way, but if you're looking at online references, instead of the if rising edge of clock, you will see it written, how do they do this? Sorry. If clock apostrophe event and clock equals 1. This is the same thing as saying if rising edge of clock. The apostrophe, the tick, is accessing properties of this signal. Event is a property that is true if clock has changed. So the process runs, it says, as a result of this process running, did clock change? Yes. Did it change and now it's 1? Yes. Okay, right? It's just saying it did this, 0 to 1. There was a change and it ended at 1. There are other properties that we'll learn about that we can access using these apostrophes. You can do things like size, how big is this signal, how many bits are in the signal kind of thing, right? If you've programmed much in like Python or other languages, you can ask for like the size of an array. You have that same kind of thing with these properties. But that comes in a little bit later, actually. I just want you to be aware that if you see this written, you know what it means. I don't write this way because I like just writing rising edge. Okay. We can also build, this is actually going to be really fun, and I did this for the other class down in the lab, and I don't know the best way to introduce it because it is a little complicated. Are we gonna fight a race? So there's a new device that I need to introduce. And that device is, we've mentioned it before, but let's talk a little bit more here, called shifters or shift registers, okay? Where shift registers are going to be something like, the easiest way is just to build them out of a D flip-flop. Okay, there we go. This is the shift register. All it's doing is at each rising edge of the clock, it's going to take some data in and store it in the first. Then the next rising edge of the clock, it's going to take whatever is in the first and pass it into the second and bring in the new one. So conceptually, it's going to look like this. At time 0, it's empty. At time 1, let's say that we bring in a 1. At time 2, if the next number on the data in is a 0, then we would have this 0, 1. And then at time 3, if it was a 1 again, we would have a 1, 0, 1. And now data out is finally valid with a 1. Okay. This basic shift register, this is the simplest version that we have, which is, it functions as a queue, essentially. Let's do this, now that, now this, what's the order of things that it wants to happen. And so it can just create a queue of things. There's some issues with this one in order of queuing, which is if the data in is not valid, if whatever's coming in here isn't ready, but you need to shift the next one out. When you do that shift, you bring in invalid data, which is then get passed through, and you have to keep track that, oh, at this clock cycle of the output, we just throw that number away because it was bad. We had to bring in a bad one. There is shift registers that are really cool and really difficult to design, if I'm perfectly honest, which are cross clock domain, which is, what if you have two different components, and one of them is running at 100 meg, and one of them is running at 10 meg, or I'll give it the full units, right? This one is going much, much faster. But let's say this one kind of comes in spurts. It's like, here's a bunch of data and then wait. Here's a bunch of data and then wait. Well, we could build a device that is a shift register that is going to take an input and it's going to be able to queue up at 100 megahertz and transmit out at 10. This is really common use for shift registers, which is to cross the clock domains, which is how do you make two things talk? And we'll get way more into that in digital systems because this is a sophisticated component to build. But this is really where shift registers are going. But this is the basic version, which is just a simple queue of what's next. Yeah.
You just scale down the timing just with your clock for the shifter. 100 megahertz.
Kind of. It's actually more complicated than that. Let me look at the time and what I have to do left before I get into that explanation. No, that's okay. We can talk about it. So let's suppose that you had an 8-bit cross-clock domain register. We'll see if it ends up 8 bits. I'm a terrible artist. Okay. There we go. We're going to think about it like a wheel. Okay. And what happens is we're going to have two different pointers, two different indexes, which is where do we read from and where do we write to? So what it does is we have some basic logic that says if read and write are equal, if the read location and write location are the same, then we're going to output a signal and we're going to call that empty, right? Because it's empty. If they're the same spot, it's empty. Then if I write a value, let's say I store a 1 in here, then the write index will update. Now we're not empty. There's a 1 here. If I read, the read index will update. This 1 will stay there, but the empty signal arises. So we read. Now it's empty. The reason the empty signal is important is because if the device that wants to read sends a read request and it's empty, then it will basically go the wrong direction, the right will, and it will now look full. And so it's this kind of dance of if we write 4 times, then we would do 0, 1, 1, 0. And now my write index is over here, and I can read those. So it's just
the right index be the next one on the next blank one.
Oh yeah. Yeah, where are we writing to point? And as long as there's valid data to read, we can read through it. And if we keep writing and eventually end up here, now we would send a full signal.
So it limits its speed based on when the write hits the
Yeah. Yeah, it's just this back and forth of one of them can fill it up, but eventually it has to stop filling up and pause its processes, and then the other one will slowly empty it out and then catch up. These are tricky because the why this is complicated, why this is hard, is what happens if you try and read and write at the same time. Right, there's the issue, and we have to build some complicated logic to make sure that works out. Okay. This is the last thing today, and I have like 6 minutes. Let's see if I can pull it off. So first off, let's suppose that I've built a D flip-flop, right? Just D input, Q output has a clock. The simplest D flip-flop. And I want to use that, and I want to build a shift register. But not just any shift register. I don't want to build an 8-bit shift register, a 12-bit. I want to build an n-bit shift register, which means I want it to be however many bits it can be, or I want it to be at the time of instantiation. We can actually do that, which is really cool. So what we do is when you have the entity, and we're going to call it n-bit shift. Normally we would have the word port here, right? And we would list the ports. We're going to introduce a new type of port called generic. And in this case, I'm going to have a generic that is going to be n. It is an integer, and its default value is 16. Then I do the ports. And we're just going to call it essentially DN, clock, reset. These are inputs of standard logic. And then we have Q is an out of standard logic vector. And here's what's fun. Now n-1 down to 0. So it can actually create a standard logic vector of a size based on the port. So when I do my port map, it's going to have two different maps. It's going to have the generic map and the port map. And if I put 16 in, it will build me a 15 down to 0. If I put 3 in, it will put a 2 down to 0 vector here. It'll just make it for me. So if I want it to be differing size, I build one component, and each instance can be a different size shift register, right? Which is really cool. And then here we'll have the end. Then we're going to have, I'm just going to put a comment that says declare D flip-flop. I don't want to write all the code for the declaration of the flip-flop. Then we're going to make a signal, and we're going to call it the internal signal. And it's going to be a standard logic vector of n-1 down to 0, right? Because what I'm building is this. I'm building this shift register. Then I need to, after the begin, my shifter 0, my first one, I'm going to call this guy S0. So my F0 is my D flip-flop, and it has a port map that's going to, this is the first one, right? So it takes data in, it's going to take clock. There's no reset on it, and it has an output Q, but that Q is going to be int s at 0, and this will be int s at 1. Okay. That's what these internal signals are for. So its output is int s at 0. So now, the current way that we would do this, right, if I were to finish this design, is I would sit and write S0, S1, S2, and I would connect int S to the input and int S0. But it turns out that's actually really kind of awful and tedious to do. So I'm going to start a new line so the people in back can see. So we're just going to come down from here. And there's a new thing. I'm going to use something called a generate statement. This is just the name that we're going to call gen shift, and it's going to look like a for loop. Sorry, ran out of room. This says generate. So for I in 1 to n minus 1, I don't want to do 0 because I already took care of the 0 location over in this first one. I'm going to say shift X, give it a name, the flip-flop, a port map of, I'm going to put the port map down here, int S at I minus 1. What was my order again? Clock, and then output S at I. And then end generate. And then my output, just like I did before, my output is going to be called Q. And it's going to, right, because I had Q, my Q is going to just relate to this int S at the end. So my output is whatever the last one is. Okay, so what this does is for however many I told it to be, default is 16, it's going to build a D flip-flop and attach the index I minus 1 at the input and I at the output. So for the first generate, I've built this one manually, right? That's the last row in the first column. The first generate will take int S at 1 and connect it to is the output, int S0 is the input, and it will just build a whole chain for me of n length. Anyways, it turns out you can build full adders the same way. You can build an n-bit full adder. Yeah, I'll get to your question. Just so you know, it is time. I'm out of time. If you need to run to a class at a different building, go ahead and leave. You won't miss anything too important. But
For the entity for the generic.
Yeah.
Are you declaring n is equal to 16 or can be?
its default is 16. So
Okay,
if I come over here and I say build a test bench for it, and in my port map, if I just write port map and do the mapping, it will be 16. However, I can instead add before that a generic map. 8. Now it's 8. So the default value says I don't have to declare the generic map. I can just let it go if it's the site that I want it to be.